Good evening and a warm welcome to the SCS webinar on the Guwahati International Airport, Assam. May I now introduce you to the moderator and speakers for today. Let me first introduce you to the moderator, Mahesh Khanapurkar, Chief Architect and Manager, Buildings Group STUP Design Forum. Mahesh acquired his bachelor's degree in architecture from Pillai College of Architecture and PG in Advanced Construction Management from NICMAR Pune in year 2000. He joined STUP Consultants Private Limited as a junior architect and currently heading the Buildings Group Design and Project Management of both STUP Consultants and STUP Design Forum. In the span of 20 years at STUP, he worked on diverse range of projects involving corporate office buildings, large-scale public buildings, hospitals, hotels, institutional and transportation projects, airports and metro stations in India as well as overseas. Now for our speakers, Mr. Anand Sharma, Partner, Design Forums International. Anand Sharma studied B.Arch Honours from Indian Institute of Technology, Kharagpur, and started the practice of Tevitia Chauhan and Sharma Architects in 1995. In 2003, the practice was rechristened as Design Forum International, DFI, with a clear intent to a democratic and collaborative work environment. At DFI, he coined the slogan of people first and constantly uses his leadership and people skills to mentor and upskill the creative and intellectual horsepower. He believes that our cities must have a distinct character, and as an architect, he lays great emphasis on including contextuality in his design responses. Up next, Mr. Hariharan Iyer, Associate Director, Structures, AECOM India Private Limited. Hariharan is a structural engineer with over 15 years of work experience in the structural engineering field. Currently leads the structural engineering practice for the Building Engineering Division of AECOM India, handling diverse range of projects across aviation, commercial, mission critical, mixed use, and transit sectors. He has extensive experience of working in India and USA with concrete and steel buildings on residential, industrial, healthcare, educational, commercial, hospitality, and urban infrastructure projects. His experience combined with his deep understanding of structural design and construction helps him with leading teams, managing project delivery, client engagement, and troubleshooting issues in the project lifecycle. Requesting all the attendees to please participate in the poll and do write the name of the speaker whom you would like to address in the Q&A session. Also do subscribe to our YouTube channel, SCS TV, where we are live now and where you can get access to all the steel construction webinars and steel construction updates. Over to you, Mr. Mahesh.
Thank you. I thank MX Business India for giving the opportunity to moderate this session on the Guwahati International Airport in Assam, with special focus on use of structural steel in the building. I give the floor now to Anand Sharma and Hariharan Iyer to take us through their presentation, respective presentations, and then we move on to the Q&A session. Over to you, Anand.
Thank you very much, Mahesh. So, Design Forum International, or fondly called as DFI, has already been spoken about in the introductions. But just by way of introducing who all represent DFI, there are three of us, we're partners, we're classmates at IIT Kharagpur. Gunmeet, I and Anuj graduated together from IIT Khanapur in 1995 and embarked on ourselves to start a architectural practice on day one. I guess we were luckier than most others, but that's besides the story. Courtesy our work, we are now present in almost 27 states across the country, with footprints in retail, mixed use, increasingly affordable housing, commercial, retail development, and now our favorite vertical to be, which is infrastructure. And because we are present in almost all parts of the country, that is our thought in 10 distinct Indian languages. The project that is being discussed here is, I was telling my daughter earlier this morning, that every architect likes to be known by something that stays after he doesn't. This is one building that I would like DFI to be remembered with. Guwahati already has an airport, but they're now building a new integrated terminal building because Guwahati is, before the lockdown, it was the 12th busiest airport in the country and already handling close to 5.5 million passengers. 7 million passengers, if I'm not mistaken, this year. That goes with the projection. So we are now building for approximately 12 million passengers per annum. There is a key word in airport design. It's called peak hour passenger. So it is originally designed for 3,100 PHP and built up area of approximately 90,000 square meters. ITA level of service being B. This is one of those technical terms. But technicality is something that I would leave to Hari. He's an engineer. I'm not. So I'll go through what was playing in the design as an architect when we were approaching this project. So like every building or everything else in the world or in life, life is nothing, but just a series of moments. Get together in this webinar. But there are some moments that you remember. So the moment when India captured the Tiger Hill, moment when this lady won the silver medal at Olympics. So life is essentially just moments. So our approach always in DFI is to create buildings which are not just built spaces that you perambulate through or move through, but buildings which evoke memories, buildings which evoke experiences, and buildings which leave you with some moments lingering on long after we have sort of exited from this building. It is very, very important in context of airports because airports are extremely very, very stressful places for quite a few of us, especially the first-time flyers. So we wanted to capture what flying means to us. So you all remember the paper aeroplane that you flew right beginning of your childhood. You all remembered probably the art of origami, folding of paper as a means of expressing yourself. So learning to fly. Of course, buildings are about scale and art. Buildings have to be welcoming. This is the screenshot of Delhi airport. There is nothing more welcoming than these mudras as a person is touching down into Delhi. It's lovely. And then there are enough examples in mythology, but this one sort of touched our hearts. So the Ikea'S, the Greek mythological figure, symbolizes for us the epitome of the human urge to fly. And therefore, he became, or she became the inspiration of the design. Something very, very crucial to this airport building. So we have sort of got inspired with it and tried to capture it in a very, very prominent form. The drop-off canopy of the airport is what inspires Ikea'S. Origami, the craft is very well known. It is dynamic. It is very, very versatile. So architects look for inspiration. We found our inspirations in origami as a tool of expression in everything that we did with this airport. Roof is obviously the most manifest part of this, but you will find expressions of origami in everything that we've done in the airport. So to bring, before we get in the design of it, Our designs generally are about creating moments. Here we have endeavored to create wow moments, hoping when it gets ready, you'll all probably traverse through this and come out saying, remembering us. It's a 50-acre site that we had been given by Airports Authority, and ACOM was appointed the project management consultant come design consultant. And we were very, very fortunate to be their partners from day one on the project. We have been architects of this, ably supported by engineering team headed by Hari, among other people. It's a 50-acre site and a building footprint of approximately 40,000 square meters. And there's a vast, expansive foreground that is called city side in airport planning parlance. There is a place, so if you see from left to right, there is place for a multi-level car park, the service block where the high side of the services come in. There is something called outdoor forest, and then there is something called indoor forest. There is a place where the two of them meet. We'll come to that when we discuss the design in more detail. There is a city side landscape. There is the funny shaped footprint of the terminal building that you can see, taxi pickup and solar parking. We are Griha 4-star and approximately 4.5 or 5% electricity of this building is being generated through renewable sources like solar. A closer shot, it's a beautiful landscape. Guwahati is a beautiful place, very close to our hearts. It is a 4-plate plan as we speak. There is the arrival level, which is the lowermost level, right down there at the bottom. There is the mezzanine, which is partially for baggage handling and partially for passengers arriving from their planes, getting down to arrival. There is the main departure level, the food court level, which is sort of suspended above the departure level in such a manner that there are double-height volumes on either side, and food court sort of overlooks both sides. Then there is this extremely ambitious and complicated roof structure, more of this later. And then there is the roof envelope itself. And if you see down there at the bottom right next to the arrival level plan, the Ikea'S is a canopy which cantilevers and straddles almost the entire frontage of the airport. Sectional perspective, transverse one, cutting across the middle of it, sort of gives you a sense. I was telling you earlier about. So Ikea'S is right there. Departure, arrival, you can see the mezzanine, and all the amenities and the wherewithal of the airport, like baggage scanners, lounges, baggage carousels, etc., are all planned. All of this there. We'll see the plan later on. It'll be clearer there. This is the other side, sectional perspective. And this is where the indoor forest is. It is a part of the airport where the indoors and outdoors almost merge. The roof. So origami is one art which sort of straddles the realms of art, physics, and sculpture. It is all. So it's a guide, it's a companion, it's a tool. And you will find this origami finding expression in everything that we have done. Roof, the flooring pattern, the column clads, the theme walls, and even if signage. This is how we started, to be honest. We started with a simple box, rectangular lid, so to speak. And then we wanted to have some fun. So we folded that to make it a stable form. We added pyramids on either side. This is where indoor forests have come into play. We added dynamism, and eventually it came out the way it has come out. There are skylights because there is light required. This is what skylights do. So they create very beautiful aura of and drama of light and artificial and natural lights. There is this city side landscape. Remember, we're building in Guwahati, and Assam is the land of teas, right? So the tea gardens worked as a beautiful inspiration for the outdoor landscape design. So you will see there is terraces of gardens that we've created on the city side. These are plateaus cut from top. So we've tried to bring inspiration from tea gardens to the outdoor landscape, and the flyovers going to the concourse have green berm on either side. There is what we're calling a Namaskar Atrium, as it's the biggest form of greeting in our culture, our part of the world. So as a weary traveler is coming down from the plane and is taking the escalator down, what he sees spread out in front of him or her is a wall, which is what we're calling a craft wall. And this is something that we are intending to leave to the local craft clubs and art clubs to change from time to time. The material on the elliptical wall is such a manner that you can actually keep working on it from time to time. Festivals. This is what it is going to be. So we have chosen to do motifs and inspirations from Northeast. Try to do some visualizations from Northeast. This will be changeable. The facade is it's an extremely complicated facade. There is glass. We've extensively spec'd out GFRC for the facade. There is fiber cement board in areas where we didn't want to spend too much money, but these are not areas which are directly exposed to travelers' eyes, like in rotundas. GFRC is a choice of facade material, like I was explaining earlier on. We're using some zinc, especially in the area where there is indoor forest, and there is a decent amount of exposure to greenery and moisture there. Now, if we had, so like I was explaining earlier, it's being manifested in roof, flooring, even signage we derived from origami. It is a little different story that airport authorities having difficulty going with this kind of signage. So we are sort of trying to bring it more to the conventional kind of signage. We wanted to actually use folded metal plates to, by default, create directional arrows using steel, but so be it. So we are using origami in facade, the retail facades in the the secure hold area done using aluminum. The baggage reclaim wall has origami facade. Check-in counters take their inspiration from origami. Even the things which are holding the fids have a cut metal style. Indoor forest. So we wanted to create an experience in which a person who's coming from the plane and coming into the Namaskar Atrium that you would probably remember, walks through a green, enveloping, encompassing experience. Because if you're coming to Northeast, you're coming to see a land which is known for its biodiversity, animals, trees, the mighty Brahmaputra. See, we wanted a person to be immersed in the experience that Northeast brings. And we didn't want him to rush through it. So you will see there is a river of movement, a trail of movement, which doesn't go straight, it sort of zigzags. And because it zigzags, it sort of forces you to look here in one direction and look in the other direction. And you're traversing through what we're calling the indoor forest, which is just a glass curtain away from what we're calling the outdoor forest, which slopes within into the indoor forest. So those are terraces going up as you go from right to left. That's what it will look like if they plant well. That's the intention. This is it's a triple height experience. It's a 28-meter high experience, and we've brought in an experience of a craft village. We're trying to give place to people, artisans within the airport, to actually. It's one thing to put art on the wall. It's quite another thing to place artisans inside an airport, quite like your Shilpgram, in which they practice their craft while people are mulling around, wanting to take a glimpse as to how a paper mache basket is made, a bamboo basket is made. So providing for space for that. It's an extremely complicated roof. Hari will speak about it later, but we have tried to do justice of it. Some images, layout plans, because everybody would like to see that. So you enter from the front at the departure level, because that is there. So you dropped off. The zone in the front is where there are check-in counters, in all 64 of them. Security checked in the middle, and then you're let out into a very large double-eyed space of secure hold area with the retail experience on either side, and boarding gates are on the extreme northwest facade. When you go on to boarding plane, food court level, as I was telling you about, is slung above the departure like a bridge, linear bridge with voids on either side. And from the food court area, you can actually go and walk onto what we are calling a catwalk, which is suspended over the indoor forest. So the arriving passenger experiences the indoor forest, and the departing passenger also has a chance to go and move around the indoor forest at a height of 15 meters, and actually be able to touch and feel the taller plants, bamboo, or trellises probably. Arrival is pretty straightforward. You come in, you walk through that trail through the indoor forest. You come and collect your luggage through the baggage carousel, 6 of them. You move through customs if you are international passengers. The domestic people come from the left side of the plan, and the international guys come from the right. You move out, and mezzanine, I was telling you earlier on about, is part baggage and part arriving corridor. This aerial view, you've all seen it on the introduction screen. Some more views I'll quickly run through. Hari is giving me a hard look. So that's the frontal image. And thank you very much. I'm done.
Mahesh, you're on mute.
Yeah, Hari, you can now take over your part of the presentation.
Right.
Thank you, Anand.
Thanks a lot, Anandji, for the introduction and setting up the tone of what the airport was. A very good evening to all the participants. Thank you for taking the time out to attend our presentation. So just let me start my presentation. Okay. I'll just get it onto full screen so that it's easily visible for everyone. There we go. So as Anandji mentioned, it is quite a work of passion that has come in, and we've tried to capture all the significant features of the area as well as the craft behind it. So from a structural design point of view, AECOM was of course the structural engineers in this. We were also the geotechnical. We are also doing all the MEP and other engineering, and including the airside and the landside works, whichever are needed. For my part, me and my team, we were leading the structural engineering portion of it, so which included all the landside works. The airside was a separate specialized team from our other division. So as part of our work, just to give a brief detail of what all was involved. I mean, of course, AI was our main employer and the client. As Anandji mentioned, AECOM was the PMC plus design consultants, with DFI as our architectural partner. So Shapoorji and Palanji is the contractor for the job, the general contractor for the job. The fabrication for the steel elements in this project are with SPCL's own team plus CDC from Kolkata. The approximate roof area is about 46,000 square meters, and estimated around 6,700 plus metric tons of steel is being used in all the areas. So this is just a very brief snapshot to get an idea of the scale at which, the engineering scale at which, the is involved in bringing this vision to fruition. So one point I think which we would like to make is this project was taken up in the 3D Revit BIM platform from the start. So architectural models, the structure models, MEP and others were also made in BIM. One of the reasons primarily being that a design that is so evolved and so intricate will need a modeling tool which can also capture all these points upfront in the design to avoid issues later on as you go detailing them and executing them. So we have been working on the Revit platform across all disciplines. So this is a snapshot of the Revit model which we had from the structures side. So as expected, pile foundations, these are all friction piles, pure friction piles, 22, 23 meters deep for most part. And the major components of the project, the terminal building, there's an Ikea'S up front, which is the signature element of the project. Then there are a couple of bridges for departure and the arrival. And there are aero bridges going off on the air side, and the underground tank substation and the STP, the service area is coming through. So this is briefly what we've just identified here. Of these, the focus of my presentation, complementing Anandji, would be on the terminal roof, primarily focusing on the steel roof that we have designed for this building. I'll take you through some of the framing plans for the other floors which are in question. So this ground floor and the part basement, which is primarily for utilities. So these are all as expected framed out in concrete. The typical grid spacing here is around 18 meters by 15 meters. And we've used hidden beams, encased beams running both ways. So it's kind of a flat slab with encased beams. So it actually behaves like a proper frame. Then the mezzanine level, which is right above the arrival level. It's a partial level, so some columns are double heights and double height spaces coming through. So then at the top, then you come up to the departure level where the bridge also comes in and interfaces with the level in. So this is also the level above which then you have the food and beverage level. As Anandji mentioned, it's a connecting kind of a piece of a area which has been planned. It doesn't cover the entire footprint of it. So if this is a section that we just took in to get an understanding of how the levels have worked, what are the different heights coming through and other things. So as we can see, we do have the basements, we have the arrival level, the mezzanines are in some places partial, the departure is another complete floor along with the bridge that interfaces with it. And above which you have an FNB, which is again partially covering floor, which is then capped off with the roof structure and the Ikea'S, which covers a lot of the drop-off area in there. So to begin with, I mean, as every project starts off with, so this is kind of a sketch which we started working off on in terms of the intent which we received from Anandji and his team as to how the structure would be, they would want the structure to look like. And being an origami inspired design, you could see all these folds. These are all mimicking the folds of the paper. Now, one of the things with airports and with such designs is you ask for a lot of large span areas so that you have a sense of airiness because these floor spaces are big. And at the same time, the aesthetics of it is a very crucial component. So we have to work more to the intent of the architecture rather than pulling them to work for engineering wise more simply. So, and the roof profile also is intended to not be very heavy because if you're looking at it from a point of view of a paper, it is supposed to be light and thin, not something that is very bulky. So the roof, the depth of the roof was expected to be very thin. So shallow beams as much as possible, keeping the whole profile thin enough was the intent and approach that we had to adopt. Just a few things, if you look at it from the inside, so we have a few trusses coming through, as Anand mentioned, so these main trusses coming through. We have some column flares which we took out, and also the secondary members in between, to as one of the things to meet the intent of the design. Now we'll go through these further items as to why these trusses are the way they are, why are the columns flared, why are the beams very shallow, and how do they span, to get a further understanding on how this roof and the other elements came to be. So as is typical in every project, there's architecture, there's engineering, and the construction part, and all of them have to work together in coordination to be able to realize the project. So from an architectural point, maintaining the intent without diluting it, and also providing large column-free spaces, using shallower beams to keep the roof profile as thin as possible, and working with non-symmetric or non-rectangularly aligned grids. I mean, that was one critical requirement which we had to work with, because this is not a very traditional design. So we have to adopt a non-traditional approach. From an engineering, structural engineering point of view, a lot of it was code driven. It's an important structure. I equal to 1.5 was a standard approach. Guwahati is zone 5, India's highest seismic zone, as well as the one where a lot of tremors are seen quite frequently. So that risk is an ever-present, let's say, ever-present act of nature. So we always have to cater for it. Equally, it is also has one of the highest basic wind speeds in India, about 50 meters per second. There's only 55 meters per second, one zone which has in some of the coastal areas or some of the mountainous areas in the Himalayas, in Kashmir, Jammu Kashmir. So wind and seismic are both on the pretty much the highest zones that we would be designing them for. And in addition, as mentioned, the spans are large and also irregular, and they are not typical. We don't have much modularity to work with. So we've eschewed the approach towards modularity in the overall layout, and we try to focus on bringing alive the profile which was shared by the architects for us. From a construction standpoint, some of the challenges are long spans typically entail large trusses coming through. So there's a lot of weight that goes into it. So some kind of thought has to be given on how we would want to put this together. Of course, the contractor does it as the specialized agencies, but we would also, as designers, have to keep some of that in mind so that we do not have a very difficult design to be executed. Ductility requirements are mandatory, being the highest seismic zone in India. So detailing has its own challenges and complications. Satisfying codal provisions have their own challenges. So those were also dealt with in our design approach. So to some of the major ones, to summarize, like I said, slim profile of the roof. So we don't have any major secondary trusses, nor do we have major tie beams coming up between the trusses. The origami profile of the roof, so you have a lot of these inclined grid positions that are coming in. Some of the secondary members that span between the trusses, they are also, there is no uniformity, in which you will see in the framing plan in the next couple of slides. So there is hardly any scope for modularity, and we didn't try chasing it in our effort to design. Zone 5 seismic requirements, quite standard. Again, high wind speeds, as mentioned, 50 meters per second. And the roof profile with its gentle undulating ridges and valleys that get created, it really, rather than being a pressure, it induces a lot more suction than pressure in it. So there are a lot of places where you have actual stress reversals coming up, which has to be catered for. Different floor plate outlines means your columns are not always continuous. Sometimes you have double height, triple height columns, or even single height columns. So your roof is being supported on a set of columns of which do not have the same stiffness, which is an important thing in the design of a roof or any building. So that is also taken care of. Ridges and valleys, as per the origami profile, a lot of these ridges and valleys had to be coordinated very intricately along with the architect and our plumbing teams to get the drainage of the water out of it. So just as we have seismic and the wind as the highest side, Guwahati also gets one of the highest rainfalls in the country. So we had the trifecta of all the extremes. Another challenge based on the profile, because the paper is laid out as if it fans out, all our valleys more or less meet or go towards the same central point or towards the central line. So getting the trusses which are aligned along the ridges and valleys as the primary members, getting them all to meet at one location is also a challenge. So how did we go about, coming up with these challenges as well as these, let's say, compulsions that have to be met to ensure that the design intent stays true? So we, as I said, no secondary trusses. We used secondary frame beams. We used wide parallel flange beams. So they are about 0.7 to 700 to 900 mm deep. There are ridges and valleys which are coordinated with the framing on the bottom floor, which is the ceiling, the false ceiling that comes below. Inclined grids, again, lower floors will have a lot, there's no repeatability coming through. The ridge and valleys are fashioned in an inclined manner. So we have tried to follow these lines and put in columns where it is feasible to ensure that areas where it's clear spans are needed, they get those clear spans. One of the interesting things for us as an exercise was the trapezoidal truss, which we used to get into the roof framing. We explored quite a few options, and we'll talk about it a bit more in detail. So that was actually one of the key things for us, which helped the engineering part of the truss. The second thing which helped us a lot was the usage of flares. So typically the column comes up and directly connects to a truss. In here, in coordination with the architects, we were able to get 3-4 members out at the top, whereby you also get the idea of kind of a tree or a thing coming in. But structurally also it helped us quite a bit to cut down on some of these spans, as well as allow it to be used as a design feature within the interior design. There are some cross trusses which have been used right at the valley collection point, so that all the trusses do not have to come in right at the end, but you could stop some of them further away from the joint and then transfer them over. And the loads are getting taken care of in the detailing of these junctions. Given the spans that they have and the depth restrictions which are coming in, we had to end up doing a lot of these members as continuous members. It would have been preferred to do it as a single or a simply supported spans, but the design here was the constraints of ensuring that the intent is realized meant that we had to go for a continuous secondary and primary system. So coming to the challenge of column location, so this was the floor plan that you would see from a structural standpoint. So these were the grids 18 by 15 by 18 meters, as we see, 18 meters horizontally and 15 meters vertically on the slide. So we also have 2 expansion joints as part of the concrete design, the concrete structure design, which invariably get mandated to take care of our temperature and shrinkage stresses. We explored the option of possibly connecting the roof as one monolithic structure, but the challenge was too much for us to cater for within the design and stay true to the intent. So the columns have also ensured that they follow these expansion joints, and the roof design also caters to the same. Departure has only so these are actually double height spaces coming through, some columns coming up, which I mentioned. So now when you come here, this is what I meant by the column location. So none of these columns that you have are in any particular rectangular grid that we would like to have, or even if they have some pattern coming in, the spans, they skipped 1 or 2 spans. So there are large spans coming through. So keeping in line that this is a folded paper kind of a design. So all the ridges and the valleys are marked out with main trusses, which are fanning out from the central point and the central zone here. These secondary beams are then used to span between these trusses to be able to support the roofing structure, as well as have any support for the false ceiling structure that would come in underneath. And collection points. There are multiple collection points which have been planned as per the erosion valley profile. So we have also made sure that the drainage points and the gutters are also taken care of within the framing, and that they are clear and adequate for the design requirements. So a snapshot of what the truss, how it was. So truss is a trapezoidal truss. It's about 2.25 meters deep and similarly wide, but at the bottom, it narrows out. So the top and bottom chords of these trusses are UC 254s, and hollow sections have also been used as part of our internal, the bracings, that the vertical ties and the bracings of the truss. The secondary element is a wide parallel flange beam, 700 to 900 mm. The columns which support these are 600 dia steel pipes. A few of them are hollow. Some of them are where the loads are quite high, or where we needed a bit more resistance. They have had concrete filled pipes in there as well. The maximum spans for the truss which we dealt with in this is around close to 43 meters. And the maximum span of a secondary member in this is 27 meters. Not all of them are of this length. As I mentioned, there's a varying depth and varying spans going through. So these are the maximums that we came up with. The roof type is the standing seam with insulation roof, the 7-layer roof, which an aviation terminal typically has. And the roof supporting system for the roofing is box purlins. So square hollow sections have been used to meet the requirements of the roofing support. So a little bit more in depth with what we have. So these trusses, so if you say the plan is symmetrical along the center line of it, we have taken primary trusses which go from the central point to the farthest point. They do cross the expansion joints. And as mentioned, we also take in the UB sections between them. So you have a UB section which spans about 2 to 3 meters at the centroid, if you would say. And as we go further and further apart, the spans increase. So there is not much repeatability coming in. So there have been some optimizations that we've tried to bring in terms of the member sizes. The second set of trusses actually end up bounding the periphery of this roof profile, because these long trusses, the ones marked in purple, truss 1, they also end up transferring a lot of load, which needs to be taken in or transferred further to the columns, because the ridges and valleys did not align always with columns. So there are quite a few ridges and valleys which are supported in this fashion, where long span trusses were needed. So these have come in, and we have put them in along with it. So the typical spacing which we adopted to the secondary members was around close to 6 meters. We experimented with 5, 7 as well, but 6 turned out to be quite a good number for us to be able to support the roofing membrane at the top as well. Now, coming to the truss, which I spoke about, one of the key things which we did. So we actually ended up starting up with a single, planar trusses going all the way to 43 meters, which is the longest, as well as 20-odd meters, which was more common in some of the areas. One of the challenges which we found was, of course, the sizes were quite high because of the depth restrictions, but we also started needing a lot of ties to the compression element, which was the top chord in a regular gravity situation, which gets ties from the roofing purlins. But in a stress reversal scenario, which was also very prevalent given the wind actions, we were having the bottom chord going into compression, and we were not in a position to take ties, because the nearest member from which you could tie would be probably 10, 15, or even 20 meters away, because there would be another truss. So the next option was, okay, since you don't get much ties, what could we do? We could probably go to a box truss. Again, the problem with the box truss was it was working fine, but it takes up a lot of area for us. And the design intent of a ridge and a valley with a narrow profile and a clean profile would not be satisfied. So the two of them were kind of merged, whereby the bottom of the truss, the two chords were put back to back. And this ensured two things. One, the profile was slimmed out so that it fit in within the roofing profile coming in. And we also had enough out of plane resistance during the stress reversal cases, so that such that we didn't need many ties at the bottom chord. So that allowed us to fit within the intent, where without having a very huge or bulky structure coming out. So some challenges, and you also start to see some more diagrams from here, which should help clarify a lot of what we have done. So we had a challenge which was there was in terms of shallow depth, which is very difficult to fabricate, or the other option was having a UB or a WPB member going through. But we also wanted to ensure continuity, which is what we were trying to get in. So in this, we ended up having to cut slots in some of these truss cord members to ensure, not truss cord, sorry, the white parallel flange beam members, such that the truss would go continuous and the wide parallel flange beams would be continuous along as well, using the splice connections at the top, so that their depths would be within the 0.7 to 0.9 meters, which we had worked out. So that was another kind of an innovation that we had to end up working with in order to allow for the depths to be restricted. Then general challenges that we have in the roof design and detailing. So for example, we have some portions where it covers everything, including some of these front portions here. And this is a big, large, long section that we have. So you have very large spans, but fortunately you also have some expansion joints in some cases coming through. So we had to deal with all these scenarios coming in. There were also flares which started coming in, which was an evolution within our own need to cut down on some of these spans and ensuring the depths of these trusses were manageable. So the flares worked to allow us to get down the clear span between the trusses to a lesser amount, which helped to reduce the truss depth and which helped meet the design intent. There are also quite a few large cantilevers at the corners and at some of the edges of the truss. So they were upturned in line with the slope, and then that acted as some kind of a pre-camber for us to be able to control deflections, as well as give some depth to control, to generate the stiffness required, to take care of any vibrational issues that would come in from the wind impact that would follow. Again, a more detailed view of how things would cross through in some of the bridge and other areas. So here we have one of the roof truss elements, which is covering from the terminal area, crossing over the departure floor plan, and it goes all the way across the drop-off bridge that comes across. So these are the drop-off areas. So the bridge is separated from the main structure, and we also have the bridge separated on the other side. And we also have what is called, to cut down this large span and make it manageable, an intermediate column which is taken off from the bridge. But we didn't want it to impact or interact with the bridge in a manner where they would start influencing the designs. So there are isolators or pads kind of thing which have been detailed in that allow only the transfer of gravity, but any kind of lateral forces are taken up directly by the trusses onto the main structure, which ensures that the bridge is not adversely impacted. At the same time, the roof truss is having a vertical support, which allows it to reduce the depth of the truss that we would do. The corners and the flares coming to one of the major things. So this is a central point where we had close to 6 to 7 trusses coming through as part of the ridge and valley scheme that comes up. Now, if you have these many trusses and all of these trusses are typically 2 meters wide coming through and collecting at the same point, it becomes very difficult to coordinate the connections. So we ended up having to space them out further apart using these supporting trusses, as well as the column flares which were coming in again. They came out further apart and started picking up a couple of trusses at these ends, which allowed for the valley point to be decongested as well as allow for any of the service coordination that would happen, and also help during fabrication and erection. So this is a typical truss profile that we would have in the column location. So to support the flare angles, again, as much as we keep saying it's a flare, they are also not always very common or single one. They are very specific to each location or to each ridge and valley location. So the angles vary, the lengths vary, which necessitate a more careful detailing and more careful design of their connections, for which the contractor has been working on it, and it is not easy from what we have seen so far, but also it's not impossible. Being engineers, so we will come on to some of the analytical model that comes in. So from the analysis model, we created a simple stick model in STAT to begin with, and we started putting in our column loads and other things coming here. So we developed it further on. We ran some optimization studies to be able to put the members where we really required and not where they were not required coming in. So modeled out in 3 and 4 parts as per the seismic joints that we had. And these are the indoor forest framing coming through. And this is the central spine zone, which connects the 2 halves of the terminal. So some deflection profiles, which is quite interesting to see. Given the large spans and the framing that came in, it was essential to control a lot of the deflections from the self-weight itself and the gravity load itself. The earthquake and wind had their own challenges, but even the self-weight was quite a challenge in itself. So if you could see the profile here, there is a significant deflections at the edges and the corners as expected. And these kind of framing was optimized further. We had about close to 7 or 8 iterations to be able to reach this framing plan in order to stiffen up the edges and the corners to have the deflections within the limits. Some of these trusses had pre-timbers being made in to be able to meet the deflection requirements. Again, large span cantilevers or end cantilevers coming in, they generate a lot of bending moment, a lot of deflections. But the natural angle in here as part of the roof profile also helped us acting as a camber, which coupled with our design, we were able to reduce the depth and keep it within the design intent. There are a couple of snapshots here these are more of actually detailing snapshots that are being developed further along with the steel contractor, but these go to show the kind of effort that is required to realize an iconic structure of this type. I mean, these are not standard run-of-the-mill typical connections that you would see in an everyday project. They require a lot of effort and coordination from the design team, from not just the engineer, but also including the architecture, because a lot of these connections or these elements are exposed. One of the beauty of steel is you can help expose all these elements. So these are required. There are also a lot of anchorages and embedments that go into concrete, because the steel roof is supported of concrete. So you need to coordinate within the available concrete element to be able to support and connect your steel member. There are restrictions on the size of concrete elements as well. So that becomes a very critical aspect of coordination and design and detailing. Just few snapshots of where and how these are all taken from Revit, by the way. So this in a way also ties in with what I mentioned at the start, that the use of Revit was inevitable for us, because there would possibly be no way that we could complete a project of this size and scope and design within a short period of time that we had without the use of a 3D modeling software that is available across disciplines to work with. Some more snapshots to see how we coordinated we ended up modeling expansion joints, the roof that would come in and merge with each other, where we were able to design or detail their cutoffs. There are some facade elements hanging off from the roof and being supported off the roof, which are also being modeled. Now, this is the signature part of the Ikea'S, which it starts off right at the front the first thing that you see when you approach the airport, and it covers the departure bridge as it is. So Icarus by itself, I mean, if you see, it's mimicking the wings that are coming in, and there are hardly any supports that are there by design. Of course, you can't have a wing being supported every 10 meters. So because of this requirement, structure had a tendency to kind of fall on itself. Not literally fall, but its manner of speaking. So we had to end up designing a lot of stiffnesses along the tension side, along the compression side to find out how it would behave. And those elements then were stiffened up. For example, in some portions, in the central portions, you would see the Icarus to be highly slanting and cantilever with a very support at the very fag end of it. But by nature of the shape, it would try to straighten itself out, generating large thrusts both at the base and at the top. In other areas, as you move further towards the tip of the Icarus wings, you would see that the cantilevers are more manageable in a sense of shape, but the span reduces or span changes progressively. So there are challenges with stiffnesses, there are challenges with lateral stiffnesses as well. So we worked out many options. It's kind of a space frame, kind of a truss which comes in, which ultimately worked out for us. And there's a lot of piling also, which was we ended up requiring, because the uplift forces purely from a gravity perspective as well was quite significant enough. And being pure friction piles, the number of piles had to be quite significantly higher. So all these was done, and we were able to get the framing of this sorted out. So as we mentioned here, and one of the key things here is that we have a tie between the two wings. Without the tie, it was becoming very difficult for us to be able to manage and support this member. So this tie effectively, it's a pure tension tie under all conditions. It was the one which was allowing us to keep these two in place within the manageable structural element sizes. So the major arms or the major legs, which is another space frame truss, there are 3 trusses coming through, and these trusses themselves are trussed together using further ties, and more like a lacing or a battening kind of a situation, not exactly battens, lacing more like it. Again, the view of the analytical model. So as you could see, they have the wings coming in and everything, but the amount of supports that we have is very, very shallow or very few. The number of supports on one edge is high, but the other edge we only have 4 supports, and there are large spans which are unsupported and large cantilevers coming through. So they ended up influencing the gravity behavior of the structure itself very significantly. But we were able to manage it out. There were significant deflection issues, which, as we could see from the deflected shape of this model, which is plotted as a snapshot, and we were able to meet it within the code limits, as well as ensure that there is sufficient stiffness to meet all the requirements. So further, more details, some of the force diagrams and some of the friction profiles which we get. These elements were a little bit more easier for us to deal with. They were not challenging, and because they had a tie that was coming in from the departure bridge side and the departure floor level side, whereas the central portion in the previous slide, which we mentioned, was freestanding from the ground to the top of the wing. So I'll close this presentation out with a few site photographs. The work is ongoing at site. It's still some ways before we realize this project into but it gives you some of the idea of the steel fabrication of the trusses which have been going on, the trapezoidal trusses, which we talked about, and some of the anchor bolts, the number of anchor bolts and the pattern in which they are laid out. That should kind of give an idea of the complexity and the challenge that is present in undertaking our design. Not the design, but actually in the ideation, the design, realizing it, and construction. So it's a work in progress. We will be there, and pretty soon we hope to have this fully done and completed and up for operation. Thank you.
Thank you, Hari.
I'll just make a small announcement, requesting all the attendees to please participate in the poll and glance through the interactive magazine of the SSMB, link to which will be in the chat box. Also, do write your feedback to edit@mxbm.in. Thank you. Over to you, Mr. Mahesh.
Thank you so much, Hari, and thank you, Anand. I'm able to look at this Q&A session, and most of the questions are on the technical aspects. So, Hari, you can take a 1 minute break and have a cup of water while I'll just ask a few questions to Anand so that Hari can regroup. So, Anand, first question that comes across to the mind is, the building has a unique shape, origami. How challenging was it for you to get it approved from airports authority who are used to, either flat roofs or curvilinear roofs? How challenging was that?
So this project's concept was approved in 40 days flat. And in first presentation, I remember there was Mr. Raheja who was the member planning. And we presented it to him on 21st April, I still remember the date, 2017. And June 16th, it was cleared by chairman. And the then Minister of Civil Aviation, Mr. Ashok Gajpati Raju. It was not difficult. It was a dream come true. And every architect's dream come true. Client takes his concept or her concept without any too much interference, so to speak, if we may call it interference. But it was flawless, smooth, dreamy.
Okay, that's indeed encouraging to hear about the approval process. So I'll take some questions to you, Hari, now.
Yeah, sure, Mahesh.
Yes. The origami shape of the roof is indeed interesting. Did it help to bring in structural efficiency, like folded plates bring strength to the structure?
I would say yes, Mahesh. In some ways, the folded plate structure was what we were trying to mimic, but except instead of a shell, it was a steel beam. So steel, obviously, we would like to keep it more as a skeleton kind of a structure. So ridges and valleys and the spanning beams helped us out. So yes, it helped out in the fact that it was an efficient design for us, as opposed to something that would say be a curvilinear roof or other parts in similar profile. And all these were geometric. I mean, if you see, and something maybe Anandji can help us, can add more detail, is there were no curves or something within the roofs. A lot of them are primarily all angular or geometric, and they're all linear. So that also helped us out with a lot in terms of detailing it, because steel with curves typically is, it has some challenges in it, so which we didn't have. So that was good for us.
So, so you felt the steel consumption was efficient than a curvilinear roof for the same footprint of the roof? Or...
They were pretty close, Mahesh, actually. We've had a couple of other projects, of a similar scale and scope going on simultaneously. So they had, one of them has a curvilinear profile, a pretty drastic curvilinear profile. So when we compare these consumptions between the two projects, I mean, there's not a huge difference between the two.
Right. Okay.
But having said that, just so that I clarify, having said that, the spans are slightly different. That had only around 30 odd meters of clear span. This is close to 43 meters. So
right.
It does make sense, but yeah, it is not very drastically different.
Very okay. Then other question is, the roof has a lot of folds. So how did you manage the roof drainage, gutter and downtakes? Did you have downtakes within the terminal building, or all the downtakes were taken through the suspended ceiling onto the edges of the building?
So I'll take this question. So it's a galvanum sheeting roof. We are attempting to do aluminium, but because of budgetary constraints, we could not go there. So there are gutters and aluminium, of course. But the primary method of drainage is siphonic. So we are not doing gravity drainage. We are doing siphonic drainage. We are collecting water at perimeter only, and water by the virtue the design is done in such a manner that water goes to collection points at one of those. So there are large columns on the Ikea'S side. There are large columns on the air side. There are collection chambers there, and there we have functional siphonic downdrain drainage pipe and a secondary, additional backup drainage downtake pipe. So we are doing siphonic drainage, and therefore slopes are really not a consideration. We're doing all drainage perimeter, peripheral.
Peripheral. So this one is for you, Hari. What is the lateral load resisting system that was adopted for the design?
So for a building, I mean, this is always a question that comes up for all such airport buildings. So for the terminal building by itself, the floor slabs and the up to the departure level, which is the concrete portion of it. So these are ductile moment resisting frames, special moment resisting frames. Once you start getting into the roof, it becomes challenging because of trussed columns and other trusses and columns coming through. So there we ended up using a standard response factor of around 3. Into the design, we got a 10, and we were able to design it as, even though it was designed for a high seismic zone, we took up and we detailed it all ductile, but it was designed considering a non-ductile or a very low ductility system, which is quite typical in a roof of such manner.
Right. So you didn't have any shear walls or any such elements there?
Very few. There's hardly any scope for shear walls in very few places, but not much shear. Yeah. So lift cores are very few and far in between. Escalators are more prevalent. So shear walls are very, very rare. It's not easy to get shear walls. So moment frames were the choice of lateral system. Special moment frames designed and detailed for 13920, the new code.
Okay, right. One related question is, did you perform any kind of wind tunnel analysis?
Very good question. Something that we had suggested. Unfortunately, it didn't go through. So we ended up on the extreme side of conservatism towards evaluating loads and other things for the wind so that we don't have any issues later on.
Okay. Okay. Then, Hari, we realized when you explained us about the columns and the roof truss design that the flares in the columns were a requirement to cater for the structural design. Anand, was that conceived originally in your design also, or it was something that you had to adopt during the design process, or accept as a change into your ideation?
So so it's an 18 meter by 15 meter grid for the plan, and in the concrete portion, which is the arrival roof, the concrete levels up to 15 meters are all pretty straightforward rectilinear concrete grid. But thereafter, the origami roof follows no grid. Right. So we could not, we didn't want to take all columns. The original intent was to omit at least an alternate column on either side. So we were looking at a 36 meter by 30 meter column free space for the steel roof. And Unfortunately, our structural engineers wanted columns, right?
We didn't ask for too many columns, just a few columns.
Yes. So we gave them columns where we could, and because of the new code thing, you can't have a floating column. We couldn't do stuff. So we couldn't do stubs. The columns, wherever they are all on the grids, right?
Okay.
Now, there were places where they could do a column only on the grid, but the truss was going a couple of meters hither or thither. Now, how do you manage a truss which is not falling exactly on a grid, which it was not? So you do flares. So sort of flares came as we went along in the design. We fought a lot. We tried to minimize as many flares as we could, but wherever they eventually sort of, raised their hands and said, no, this is definitely needed. Then we tried to create a symmetry and a form around there. So very interesting places where so many trusses are meeting at one point, right? And there we have flares, and then we have treated very beautifully the entire, using that ST truss that Hari was talking about. We made that into a very, very beautiful design element using false ceiling. Yeah.
Right. Interesting. So one question for you, Hari.
Mhm.
Parts of the structure are separated at expansion joints. They will behave differently for seismic response.
Correct.
Each part will have a different natural period and deformation. How was this considered in the design and detailing?
So for the concrete structures, it was quite straightforward. They were all modeled and analyzed and designed as separate structures, and the gaps that needed to be given in, as per the building code, are multiplied by the R factors. We put them in. The roof was an interesting part. We tried to have the same approach for the roof as well, but you have to appreciate the roof is on top of a building to begin with. So your building moves as it moves, and then the roof moves as it moves. So there were challenges in getting it, but we still managed to have the same approach with the expansion joints coming in. In some places, especially near the front side drop-off areas and others, there were challenges with the trusses and the coverings going across. So we ended up having to take some vertical support just for the gravity purpose. So that's where some of the STUP columns started, or not exactly STUP columns, but columns which started coming in from the bridge structure. But since we didn't want it to connect it, we had some of these isolated joints. So the lateral movement is taken care of or allowed free to move for the most part. Only the vertical load is taken up. So that's the strategy we were able to adopt and get in to have all these different parts move together and on their own without clashing into each other.
Right. The one related question is, what's the distance between the expansion joints, and how are they taken care in the design of the roofing system as well as the suspended ceiling system?
They're about 115 meters apart. We have approximately 150 meters by 250 meter, 280 meter long building. So they're about 100 meters apart. There are two expansion joints on either side of the center line.
The question is, what was the width? I mean, how much was the width allowed for a maximum expansion between the? What was the joint width?
The joint widths varied at different levels from, I think, around 75 mm to close to 250 mm at the top. So they were different, depending. And we also didn't want, so the design also had to take care of, the ensuring that the joint widths don't come out to be crazy wide. Of course, we could optimize the structure such that it has the least amount of framing going in. But if the structure is going to move half a meter or something on each side, it becomes a big problem trying to, or rather a challenge meeting those. So there were a lot of restrictions. Around 250 is where we ended up, 250, maybe 300, I think, which is the final number at the roof. But we started off with around 75 mm at the bottom levels and progressively increased it above as we went up the height of the building at the different levels.
Okay. You mentioned that there are some columns in the building, especially the steel columns, which are filled with concrete.
Mm.
So, do you also, are they designed as composite columns, and whether there was any reinforcement used within the concrete?
They are designed as composite, but not in a full nonlinear composite manner where every strain and everything is taken. And it was more of a. These columns are filled out with concrete primarily to increase some amount of compression strength, but a lot to take care of the uplift forces which are coming in some of these places. So we ended up, having this dead weight to counter them. So a lot of these column filling were due to that, as well as the reinforcement was the basic reinforcement that we needed to ensure that there is no shrinkage and other cracks going into the column. So that was it. But they are not true blue composite columns that we would, design them including studs in between to ensure that concrete and steel act in one manner and the strain compatibility is mentioned. So those things, it is not a true blue composite column. It's more for their means to an end for those particular locations.
Right. Then another question is, you have long span trusses. So how are the splicing details? How many splices you had, and whether you had any challenges in erections?
Well, we don't have any challenges in erection yet because erection has not started at site. We will find them as we go. But yeah, design-wise, there have been quite a few challenges, especially with splices. Splices typically depend upon where the fabricator, how much they would want to fabricate in one go, and with the erection of how they would want to erect it. 12 meters or so has been the average spacing. They are typical splices designed as per Chapter 12 of IS 800, and along with the full brunt of, as I could say, the brunt of ductile detailing requirements. So joints are pretty heavy because they are bolted joints. These splices are bolted joints. They are not going to be welded in situ because that brings its own challenges. So because of the bolted connections with the full 100%, 120% strength requirements that come in as per the code. So these are all bolted joints, HSFG bolts. They are quite massive, but inevitable.
Right. Another question is, IS 875-3 does not give roof coefficients for this type of roof for wind pressures. How were these calculated? CFD modeling or wind tunnel studies? Or what was your how was it done?
So that's a very good question. Something that we had identified upfront. Wind tunnel modeling or some specialized wind studies would definitely have helped optimize what we have currently furthermore. But then in the absence of that, we have to make best use of what all literature and what all resources we have. So IS 875 does have a whole bunch of typical tables on the different profiles of roofs coming through, continuous grids profile and things. So it was an exercise of studying them iteratively, trying to stitch together different conditions which are identified and as they apply to the different parts of the roof, and then trying to make another composite map or a picture of how the pressures would act as per those literature. And the literatures were also taken to be from a conservative standpoint. So that was the only way we were able to put this thing together and ensure that in the absence of a more advanced or a detailed study, which unfortunately could not take place, that we still were the side of caution, erring on the side of caution.
Yeah, and this project must have gone through a round of peer review or proof checking by a third party. So
IIT Delhi.
Was that okay? Did they have any reservations on approving this without the backup of a wind tunnel study?
No, that was fortunately enough, we were able to discuss along with them. There were quite a few inputs also that came in from their side, which also helped decipher the IS 875 Part 3 charts on how they could apply it. They were strong proponents of wanting to have a study done, but in the absence of that happening, they ended up supporting us with a lot of knowledge that we could gain from their experience as well. to ensure that, in the absence of such studies, we are able to do still be on the side of, conservative side.
Right. You mentioned that the fabrication is ongoing on site. Did any limitations on the contractor's part with regards to erection of the truss make any impact the design in any way in terms of detailing or having any other impacts on the design?
So the way this thing worked with the AI and the process, we ended up designing and detailing a lot of this building much before there was a contractor on board, and a lot of the detailing happened by the time even before the steel contractor was decided. So those inputs of how a steel contractor might want to have changed things, they didn't come through. So I would say for pretty much all the way, the design intent of what we have done carries forward. The inputs that come from the fabricator's side after studying drawings is where they would want to splice or how they would want to lift, or maybe some changes in the sequence of how they would want to fabricate and connect, and some of the welded members. So those are the kind of things which are coming in, the design of the splice connections, some coordination between the elements that come through when they start detailing out all the elements into their shop drawings. So those have been the inputs that have come in, but no, there have not been any major inputs in terms of change in the erection strategy or something, or the change in the design due to the erection approach or the fabrication approach that the steel contractor would have wanted.
Right. Was Tekla used in the steel modeling, and or you had developed this entirely on Revit?
So our part was on Revit, and we have a bunch of models and all which were handed over for further working. So the design and detailing part from the steel contractor's side also was working, I believe, on Revit, and there was some bit of Tekla going through it. So I'll have to check furthermore on how much of it is gone. We've not seen much. We're still fixing out process by process going through on all these. So hopefully we'll start seeing a lot more drawings and details as we go forward. When things come up to us, we should have more clarity.
Right. Then, where the main truss is crossing over the expansion joint below an RCC, designed to be flexibly supported on the columns?
Not all of the trusses are going through across the joints. I mean, in many places they do terminate, there are physical gaps. In the places where they were crossing over, like in some of the front side where I mentioned they crossed over the bridge part of it as well in some places. There, yes, wherever they took a stub support from the bridge, the top of that stub had a isolator, so that laterally it was not restraining the behavior of the roof. It was just a vertical support.
Okay. Then, are the structural elements welded, or it's a bolted connection?
It's actually a mix of both. Some of the major end connections for these trusses, where they go in, they are bolted. Splices are bolted, but interim within these members, they are all welded. So it's a mix, actually. It's not a fully welded structure, because welding structures of this size directly onto the site is also a challenge in itself. It brings its own issues. So that's how it has been.
Okay. There's one question which probably Anand can take. How many schemes were made and presented before, alongside this scheme, which is having a origami concept?
So we had 3 schemes that we had presented to Airport Authority. And this one was the most complicated. They chose to go with this on day 1. And rest is history. Just 3 schemes.
3 schemes, right. Then we have a question for Hari again. For large concrete cantilever beam deflection, check was done only for dead and live loads, or lateral load combination were also considered?
There were no large concrete cantilever beams. They were all steel frames actually. But yeah,
sorry,
I
steel.
believe, yeah. So they were not just there. We checked out for all the load combinations. I just showed the pictures of the gravity ones because it seemed enough. We had more than, I think, 100 plus combinations which are coming through with all these plus and minus, plus x minus x and plus y minus y conditions, along with the vertical combinations which are also mandated. So yeah, they were checked out for all these codal combinations.
Right. Then another question is, did you explore the space frame option for some of the areas instead of a truss option?
Okay, so from a space frame would be something like those, the triangular grid frame option that you would see in many of the terminals which were in vogue probably a decade back, which have been built in, something similar. Is that what you would think, Mahesh?
I think so, yeah.
Okay. So those things would have also been an option, but then again, there are challenges in terms of number of elements that you have to fabricate to get the nodes in correctly. That is one. Second is, of course, the depth again, and how you would want to span them out. So we didn't actively look at it. Our approach was more of, a spine and these secondary member approach, which for most part has suited us and also helped keep the thickness of these things much slim enough.
Right. Then the question is, what are the kind of bearings and isolators that were used?
I mean, there are no basically bearings, but the isolator ones, yes, these are, we still haven't really received much details. We still have to explore it's a performance spec that we have shared. So we are still awaiting, whether they're going to be a basic rubber bearing isolators or steel plate isolators with some kind of a friction reducing material in between. So we need to see the details. We haven't yet really received the details, though we have specified a couple of these as an option that could be looked at.
Right. Then there's a question on the main building design. How many piles are driven to take the uplift forces?
There are no piles which are purely driven as uplift piles. I mean, all the piles invariably are working towards supporting the gravity forces as well as resisting any of the uplift forces that might come in. So there are no specific uplift resistance piles which are coming in. I mean,
Right. Another question maybe I have from my side. Anand, did you explore use of solar panels on the roof for sustainability benefits? Was that considered?
We didn't want to put anything on the roof. That takes away, it's a beautiful roof, and airport is one building that you would definitely see from the top. In all other buildings, we show aerial views, but nobody ever sees it. So we resisted putting anything on the roof. Right? And except for Skylights, it's a clean roof. There will obviously be communication equipment and other such stuff. Roof maintenance stuff will be there. So solar panels are all on the city side. You will probably see it in the image that is behind you. We have 250 car parks for visitors and another 100 car parks for staff and others. And we are harnessing the entire canopies of those car parks, individual canopies for solar power generation. And we're able to generate quite a bit. We're able to generate almost 250 kilowatt load using. So we have put solar panels over parking. We put solar panels over the utility blocks to some extent. That's nothing on the main roof.
Okay. Good. Yeah, I guess Okay, there's another question. Whether segmental constructions were followed here? I guess this I guess the answer would be no. Hari?
No, I don't think so. No, it has been segmental. I think is more for a linear structure, something like
Linear
a bridge or something that would come in. I mean, this is not doesn't really qualify or lend itself so well to a segmental type of construction.
Right. There's one interesting question. I think I'd like to take this. The question is, what do you have to say about use of stainless steel as a material for structural application? As many European countries are adopting it, and they prefer duplex stainless steel even for roof cutter.
Anandji would like something on the gutter, or do you want me to take on the engineering?
We would love to use stainless steel for gutters. Why not? But I think our purpose with aluminium here is amply served. Aluminium has the same characteristics, and it is obviously not as expensive as stainless steel. It would be aluminium in this case.
And from an engineering standpoint, I mean, stainless steel is being used in some of these places. Primarily, a lot of the use of the focus on stainless steel comes from the corrosion, durability, and longevity issues. You want to have maintenance-free structures. You want to have corrosion protection coming in. From an Indian standpoint, the cost that it comes with versus the benefits from a basic structural performance, we still have to evaluate it on a case-by-case basis. Stainless steel in a concrete construction has slowly started coming in, where stainless steel reinforcement is now being used. Stainless steel meshes are being used, in concrete structures and elements of concrete structures, which are more subjected to corrosion, more aggressive elements of the nature or any soil or any other materials. But on a steel basis, as a pure steel element from the normal structural steel that we use versus the structural stainless steel to be used in this place, it probably may not make sense for a lot of the projects. I mean, some of the projects which are exposed steel or something, they may have some need, or they may have some cost benefit ratio in their favor, but not for the total projects that we have here. It will be a niche kind of a material. It won't be a mainstream material as the regular steel that we have, the carbon steel that we have.
Right. No, I agree. Stainless steel as a construction material is a long way to before it is made use in the Indian construction industry. On the Ikea'S design part, there's one question. How torsion has been taken care of while designing the inclined columns of the Ikea'S?
So that is actually a very good question. That is one of the things that frustrated us a lot. And if you can recall some of the images that I showed, the column that is coming in, the torsion was primarily coming out into the central column, as we call, right at the middle, from where the Ikea'S wings grow out. So if that column was framed as not a single frame element. It had at its corners like trussed columns themselves coming out, and these trusses were then trussed together to be able to generate the stiffness. So that was a development of this resistance to torsion which is coming in. There were also cross bracings inside it to be able to stiffen it up within its plane. So that's the only way we were able to deal with it. There was no specific separate section or something. It had to be evolved through this excess of analytical options that we had to work with.
And I'm sure Anand would have resisted all his might before he gave in to connect the two elements of the Ikea'S.
Yeah.
At the top.
That was kind of the last resort for us, because
Ikea'S was, I think, the trickiest one and continues to remain.
The erection of it is also going to be quite a a thing in itself. So very interesting thing.
Right. And another question here is whether the forces moments due to the earthquake in the cantilevers were enhanced by 5 times as required by the code.
Yes, we have done all those requirements, and we have taken in ensuring that the member sizes and other things are adequate for those amplifications.
Right. I think we have taken all the questions, and I think we have exhausted all of them. So thank you so much, Anand, for this presentation, and thank you so much, Hari, for patiently answering all the technical questions.
My pleasure.
In fact, this was one of the most insightful discussion we had on the project. And I think speakers have fairly answered almost all the questions. I'm sure this is the part 1 of the presentation, because I think the construction will be equally challenged, which we can cover in episode 2, probably. And thank you, Anand sir. Thank you, Hari. And special thanks to Mahesh for, in fact, weaving this entire discussion into such an interesting format.
Amazing. So, thank you very much.
Thanks a lot for putting this together and getting us in this platform.
It was really inspiring project, I'll say, and equally complex project. So thank you so much for sharing your insight on this project. So from Guwahati, we are going to Bangalore next week. And this is one of the unique projects, Flipkart complex in Bangalore. In fact, Bangalore is the hub for steel construction, same in line of Hyderabad and Mumbai. So in fact, this unique project have close to 12 towers, which was a composite construction designed with steel. The building height varies from ground plus 4 to ground plus 11 structures. And there are a lot of unique structural elements in the design of this Flipkart tower. This was one of the most economical design of steel, which was being done by the consultant. And it minimized the number of shear walls to reduce the construction timeline. The stairways was being done with precast, and there are a lot of elements, other salient features, elements which are going to be discussed next week. The high strength steel was used. The primary frame of the building was typically 11 meter by 11 meter grid, and with the secondary beam located at approximately 3.7 meter spacing. So the large grid size with shallow beams make it one of the unique projects that will be taken up by Hariom Gera and the project management consultant, that is previously Synergy, now Kohler. So they are going to talk about this interesting project next week, same time on Friday evening at 5 o'clock. Do join us. The link is there on your chat box, and please give your feedback. And Anand Saab, Hari, Mahesh, thank you so much for joining us today. And we are definitely going ahead with the episode 2. I'm quite excited about it.
Thank you very much.
Look forward for it too. Thank you for having us over.
Pleasure. Pleasure to